Hi, I'm Max Mercer, and welcome to this lesson about linear transformations. Let's look at an example to see what a diagonal matrix actually does to the geometry of a space. We want to know the effect of left multiplying by this matrix A, which has a 2 and a 3 on the diagonal. We start with our input space and output space. Since this is a 2 by 2 matrix, we'll soon see why both the input space and output space are two-dimensional. Here's our basis vector 1, 0, shown here in purple. Since the matrix has a 2 in the top left, the x component doubles, while the y component stays at 0. Visually, you can see on the right that the purple arrow simply gets twice as long. Now look at the vector 0, 1, shown in blue. Left multiplying by the matrix means we take 0 column 1s and 1 column 2 added together, which gives 0, 3. This time the matrix interacts with the 3 in the bottom right, so any vertical component gets stretched to 3 times its original length. Now when we combine those with the vector 1, 1, the matrix operates on each coordinate independently. The x part doubles to 2, and the y part triples to 3. The red arrow shows us that the vector is stretching more vertically than it is horizontally. This works for any input, even one with negatives or fractions like this green vector here. We take negative 2 and multiply it by 2 to get negative 4. We take 1/2 and multiply it by 3 to get 3/2. So here is the intuition to keep. This matrix creates a non-uniform scaling. It takes any 2D vector and stretches the horizontal direction by a factor of 2 and the vertical direction by a factor of 3. This is for the specific matrix 2, 0, 0, 3. Now let's see what happens when we left multiply by this matrix B, 2, 0, 1, 3. To figure this out, we should always start with the standard basis vectors. So in purple, we take the vector 1, 0, which sits right on the horizontal axis. When we multiply it by b, it lands at the coordinate 2, 1. Now, interestingly, this result 2, 1 is identical to the first column of the matrix. That's no coincidence. That's exactly why we care about this column view of matrix vector multiplication. We're taking 1 of the first column plus 0 of the second column to get 2, 1, which is, again, the first column. Similarly, if we look at the other basis vector, 0, 1, shown here in blue, it gets stretched upwards to 0, 3. Once again, notice that this result matches the second column of the matrix perfectly. The columns of a matrix tell you exactly where the basis vectors land. So, because matrix multiplication is linear, we can predict the movement of any other vector. The red vector, 1, 1, is just the sum of our previous two inputs. Therefore, the red output is simply the sum of the purple and blue outputs, which lands us at the point 2, 4. And this rule still holds for any arbitrary point in space. If we take this green vector at negative 2 and positive 1/2, well, we'll run the numbers and end up at negative 4 and negative 1/2. So the grid lines have been warped, but the relative relationships stay the same. We can summarize the effect of matrix B in two ways. Geometrically, it constructs new vectors by scaling and adding those specific column destinations we found earlier. Algebraically, it gives us a formula to turn any old x and y coordinates into new coordinates based on a linear combination. Now, here's the bigger picture view of that same matrix to show how it affects the entire coordinate system. So we start with our standard basis vectors. We already know the matrix moves the purple vector 1, 0 to the coordinates 2, 1, and the blue vector 0, 1 to the coordinates 0, 3. So this highlights the golden rule of linear algebra. The columns of the matrix are literally the coordinates of where your basis vectors land. If you know the columns, you know where x and y go right away. Okay, so this allows us to map any other vector instantly, just like we see. Since the vector 1, 1 is the sum of our basis vectors, the destination is the sum of the matrix columns, giving us 2, 4. And so we can see the transformation of the entire plane. The matrix takes our perfect square grid on the left and shears it into this slanted grid on the right. The origin stays fixed, but the grid lines stretch to match our new column vectors. Now let's mix things up a little bit. Notice that matrix C is not a square matrix. In fact, it's a 3 by 2 matrix, so it's tall and thin. This tells us immediately that we're going to start with 2 dimensions, but we're going to end up in 3 dimensions, all right? Because we have 2 columns that we're working with, so we have 2 input vectors to map. So let's track our first basis vector 1, 0. When we multiply it by our matrix, we get the 3D vector 2, 1, 0. Because the z component is 0, this vector still lies flat on the ground of our new space. Now things get interesting with the second basis vector 0, 1. The matrix maps it to 0, 3, 1. Notice that the z component is 1, so the matrix has literally lifted this vector off the floor and into the air. So as the linearity holds true, exactly as we were expecting, so if we input the vector 1, 1, which is the sum of our basis vectors, we get a 3D output vector that's the sum of our output vectors. All right, so it's the sum of the purple and blue outputs. And this transformation applies to everything, including negative vectors like our green example here. The result that we care about is in the bottom. This matrix takes a flat 2-dimensional space, a whole sheet of paper, and it slices it through 3-dimensional space. Think of it like we have embedded a 2D plane inside a 3D world now. So we've looked at a few specific examples now, so let's zoom out and look at the general rule for matrix dimensions. An M by N matrix is a machine that transforms vectors from n-dimensional space into m-dimensional space. We just saw how a 3 by 2 matrix acts as an embedding tool, taking 2D vectors and placing them onto 3D space. But what happens if we flip the dimensions? What would a 2 by 3 matrix like this one do when we left multiply it? Well, instead of going from 2D to 3D, it should do the reverse. All right, so it should take 3D space and squash it down into a single plane. Now, here's the rule that you need to know about. The number of rows in the matrix is the number of elements in the output vector, because each row in a matrix vector product gives us an output slot. The number of columns in the matrix is the number of elements in the input vector, or else the matrix vector multiplication is not defined. So you can see this in our graphs. We start with 3 basis vectors in the 3D input space, but because our matrix only has 2 rows, they get mapped down to flat 2D output space defined by the columns. For example, in blue, you see where 0, 1, 0, that second basis vector in 3D space goes. That would just be along the y-axis before. But now in 2D space, it's going to be mapped to 2, 1 because we only have 2 output slots. And you could see if we were to take the point 1, 1, 1, well, let's see where our x goes, still here. Where our z goes will now go on to what we would call the y. Our old y goes on to 2, 1, adding those all together. Tail to head, we get that 1, 1, 1 by this matrix would be mapped to 3, 2, and you could check that for yourself. We've been moving vectors around with matrices, but let's give that a formal definition. A transformation T is simply a function that assigns an output vector W to each specific input vector V in the entire input space. If there's an input that does not have an output, then the transformation is not defined. If this looks a little scary, don't worry. It's the exact same concept as function notation. You have inputs and outputs. The only difference is that now our inputs and outputs are vectors instead of single numbers. Also, the input space and output space aren't required to be one dimension anymore because we generalized. However, we care specifically about linear transformations. To be linear, the function must satisfy two strict rules. First, it must preserve addition. Second, it must preserve scalar multiplication. Essentially, the grid lines must remain parallel and evenly spaced. Finally, just a note on notation. We use T for general transformations, but if we know for a fact it is linear, we often switch to the letter L. Let's analyze these rules for linearity a little bit more. The first rule is additivity. This just means you can combine vectors before you transform them or after you transform them, and you will get the same result. The second rule is homogeneity, which means you can scale vectors before or after the transformation, and the result is the same. The order of operations does not matter. Here is a very useful shortcut for checking linearity on exams. If you set the scalar c to 0 in the second rule, you see that a linear transformation must map the 0 vector to the 0 vector. If you ever see a function that shifts the origin somewhere else, you know immediately that it is not linear. Now, because mathematicians like to be efficient, we often combine these two rules into one single equation. If the transformation of a linear combination equals the linear combination of the transformations, then we know both rules are satisfied. This scales up to any number of vectors. Whether you're mixing two vectors or 2,000 vectors, the rule must hold. The image of the mixture is the mixture of the images. So let's look at this visually. On the left in our domain, we built a vector v by taking 3 of v1 and 2 of v2, for example. On the right, in our codomain, also called the output space, notice that the output vector follows the exact same recipe. It is built from 3 of the new v1 and 2 of the new v2. The grid changed, but the relationships stayed the same. Now here's the beautiful part. We've already defined what a linear transformation is abstractly, but now we can formally connect it to our matrices. The theorem states that the act of left multiplying a vector by a matrix A qualifies as a linear transformation of space. The proof is short because matrix arithmetic already follows the rules we need. For the first check, we know matrix multiplication distributes. So A times the sum of x and y breaks apart into ax plus ay. This matches the addition rule perfectly. For the second check, we know scalars float freely in matrix multiplication. So A times a scaled vector is just the scalar times the matrix product. Since matrices naturally obey these laws, they are by definition linear transformations. With many examples, let's verify the linearity by extracting the matrix for different transformations. For this one, what we're going to do is we're going to look at the formula and pull out the coefficients for x1 and x2. In this first example, this is a rotation. The top row has 0 x1s and 1 x2. So for example, if we put in the vector 3, 4, because we map x1, x2 to x2, negative x1, 3, 4 will be mapped into 4, negative 3. All right, this works for any general one. If we were to apply this linear transformation, then that's going to become by a general matrix A. We're trying to find what these A11, A12, A21, and A22 are, what numbers they are. We left multiply this matrix A times our vector x. That ends up being, by this transformation, x2 negative x1, but let's look, what is this really? x2 is 0 x1s plus 1 x2. Then negative x1 is negative 1 x1 plus 0 x2. This, if we were to multiply these out, the top row should be a11 x1 plus a12 x2. that's supposed to equal this, which means A11 is 0 and A12 is 1. Similarly, the bottom row should be A21x1 equals negative 1x1 plus, then we'll have A22 times x2. They're like terms, so we can really just look at how many A22s we will have. And specifically, because we know we end up with 0x2, it means A22 must also be 0. So here's the connection. We get our matrix. The first column, again, is where 1, 0 should map to. So if we put in 1, 0, that's going to give us 0, negative 1. That's exactly our first column. The second column of the matrix is where 0, 1 should map to. So if we put in 0, 1, we'll end up with 1, then negative 0 is 0. So we do get 1, 0 as our second column. Now, let's do this for more examples so we can see the pattern. Here we have a vertical shear. The top output is just x1, so our first row is going to be 1 for the amount of x1s plus 0 for the amount of x2s. Then the bottom output adds them together. So if we take in x1, x2 as our vector, the bottom output is going to be x1 plus x2. That means we have one of each in the second row. Now here we have a non-uniform scaling example. We double x1 and triple x2. That's what applying this linear transformation L does to the vector x1, x2. It doubles x1, triples x2. That's exactly our diagonal matrix, where you see the first row is going to be 2, 0, because our first row, our output of the linear transformation, is going to be 2x1 plus 0 x2s. Then the second row is going to be 0, 3, because we have 0 x1s plus 3 x2s in the second row of the output of the linear transformation. Now the linear transformation that swaps two coordinates, x1 moves to the bottom and x2 moves to the top. The matrix is just the identity with the rows swapped. And finally, this messy looking fraction is just taking the average. So if we take our input x1, x2, the output should be the x1 plus x2 divided by 2 in both the x and y positions. So essentially, if we had, like, for example, 3 and 4, the output will be 3.5, 3.5. All right, so this means every single coefficient in the matrix is just 1/2, because you can rewrite this x1 plus x2 all over 2 as x1 over 2, so that's 1/2 x1s plus 1/2 x2s. Similarly for the bottom row. Now, let's go the other way. Let's say we have a matrix and we want to figure out what it looks like geometrically. Let's use the first example from our table. First, we plug in points to see where they land. All right, so the vector 1, 0 gets sent to 0, negative 1. The vector 0, 1 gets sent to 1, 0. The vector 1, 2 gets sent to 2, negative 1, right? Because we're doing the transformation. x1, x2 gets mapped to x2, negative x1, right? That's just 3 examples of this, but this can apply to the whole space. All right, so if we plot the inputs on the left and the outputs on the right, we see the motion. It's actually every vector seems to have swung around a quarter turn, or we would call this a 90-degree clockwise rotation. All right, and you can see that is actually exactly what is going to happen to the whole space. Let's see together. Notice the entire grid lines, they remain perpendicular and equally spaced throughout the entire movement. This is the hallmark of a rigid rotation. We do start with our original vectors, and then we can see if you wanted to follow every single one, they do get mapped by rotating them 90 degrees clockwise. Now for the second example from our table, this is the matrix with 1s on the diagonal and 1 in the bottom left corner. All right, so let's trace the points. The first basis vector 1, 0 should be mapped to the first column, which is 1, 1. The second basis vector 0, 1 should be mapped to the second column, which is also 0, 1, so that will not be changed. The vector, for example, 2, 2 will be mapped to 2, 4 by this matrix and linear transformation applying that matrix. So for our input space, we'll have our 3 vectors as stated before. In our output space, we see 0, 1's not moved at all, so the blue vector is the same. But it looks like there's some sort of shearing going on. We'll call this a vertical shear. We have displacement by specifically x1 extra units in the x2 direction. So our y value is going to be increased in this transformation by the x1 value, which is why when our x1 was 0 for this blue vector, we didn't change at all. But for example, our x1 was 2 in the vector 2, 2 as our original vector. So that means it will still have same x, right? The x1 is mapped to x1, but the y value is going to be whatever the y value is plus 2, because that's what the x value was. We could see this transformation. It looks kind of like a deck of cards being pushed from the side to me. So notice that every vertical line stays perfectly vertical, but the horizontal lines get tilted into a slope. Here's our third example, which corresponds to the diagonal matrix we found earlier. When we plug in our basis vectors, the results are nicely straightforward. The x component gets multiplied by 2, so 1, 0 becomes 2, 0. The y component gets multiplied by 3, so 0, 1 becomes 0, 3. And then I also have 1, 1 getting mapped to 2, 3. So if we were to take the input space and the output space, notice that the direction of the vectors doesn't change, only their length changes. All right, so the purple vector, for example, stays horizontal, but it does double in size. All right, we call this scaling. We scale specifically by a factor of 2 in the x1 direction and a factor of 3 in the x2 direction. Because they're not the same factors, we call this non-uniform scaling. This means we stretch the space by different amounts in different directions. Now, please watch the grid for an animation. It looks like we're stretching a sheet of rubber. The origin is pinned down, but everything else expands outward. Alright, so notice that because the off-diagonal entries are 0, the x and y axes remain perfectly perpendicular. Our fourth example is the matrix with 0s on the main diagonal and 1s on the off-diagonal. When we run the numbers, we see a simple pattern. The coordinates just swap places. That's exactly what happens with the general transformation, right? If we put in 1, 0, we get 0, 1, because remember, the first column of our matrix is also 0, 1. If we put in 1, 3, we get 3, 1. They just swap places. All right, so on the graphs, this looks like a mirror image. The purple vector that was pointing right is now pointing up. The blue vector that was pointing up is now pointing right. We'll call this a reflection. Specifically, this is a reflection about the diagonal line where x1 equals x2. Every point on one side of the line is mapped to its twin on the other side. So watching the animation, you can see the entire plane flip over this black diagonal like a pancake. Points exactly on the line don't move at all because their coordinates are already equal. So finally, let's look at the matrix where every entry is 1/2. When we plug in our basis vectors, we do get something strange. They both land at the exact same spot, which will be 0.5, 0.5. If we plug in the vector 1, 3, for example, remember this one averages the x and y coordinates, give us our both x, y coordinates will be 2, 2. All right, so really what's going on here? On the graphs, we can see this consequence. The entire two-dimensional input plane is squashed into a single one-dimensional line. We effectively have lost a dimension. So to understand how points get there, look at these blue guidelines, okay? Every point slides along a path that is perpendicular to the main diagonal, the line y equals x. It takes the shortest route possible to get to the line. And we'll call this the orthogonal projection. It's like shining a light from infinity and casting a shadow of the vector onto the line. As you watch this animation, you just saw the entire grid collapsed flat onto the diagonal. Now, let's look at some deal breakers. These are transformations that might look simple geometrically, but break the rules of linear algebra. All right, so first, let's look at a translation. We're simply shifting the grid up by 1 unit. It looks like a rigid motion, which seems safe, but it's actually a trap. Okay, because if we ran the numbers, the math falls apart. The transformation of a sum does not equal the sum of the transformations. But there's a much faster way to spot this. We'll call this the origin check. A linear transformation must keep the origin and map it still to the origin. For us, if we were to keep a point at the origin and apply this transformation, we're going to get to, well, we put in 0, 0, so we get 0, and then on the bottom we get 0 plus 1. So we'll get 0, 1, which is not the 0 vector for this space. So because 0 is not mapped to output 0, I have this subscript just because, remember, the dimensions may change of these 0 vectors, but still it should always just be a vector of zeros. In this specific case, 0 does not map to 0, so the transformation, we immediately disqualify it. We know it's nonlinear. Now, our second example involves exponents. Here we have an x cubed term and an x times y term. Now, this one fails the scaling check. If you double the input to a linear machine, you should get exactly double the output. But here, because of the cube, doubling the input multiplies the output in the first coordinate by 8. So the reaction is not proportional, so it's nonlinear. Also, if you were to look at the second term, x2, our y value is going to become the x value times the y value. If we double the input, we're doubling both the x and y values, right? So that's quadrupling that second point. We're not going to have 2 times as much. So we have 8 times as much and 4 times as much. That's not 2 times as much as if we just took the constant times the transformation applied to our original vector. So therefore, t is a nonlinear transformation. Now let's talk about linear transformations on vector spaces of matrices. Remember that matrices can be inputs too. By the way, if you ever want to visualize these transformations, you can vectorize the matrices and do what we've already been doing. Now with algebra, let's see if the transformations defined on them are linear. So first we have the trace function. We'll take a linear mapping, well, we'll check if it's linear, from 2 by 2 matrices to just one real number output, where our linear transformation uses this first input matrix A, A11, A12, A21, A22, and outputs the trace of A, which remember is the sum of the diagonal elements, A11 plus A22 for this 2 by 2 case. So for this trace function, it passes the addition check perfectly. If we take the trace of a sum of matrices, A plus B, both matrices, we'll get the sum of the traces. So you could do this no problem. Let's also look at the scaling check. It does pass. If you multiply a matrix A by some constant C, then take the trace of that matrix. It's just like if you took the trace of the matrix A and then multiplied by C. So this is indeed a linear transformation. Now, what about the determinant? In this case, it fails. If you look at property 2, if you scale a matrix by C, the determinant scales by C squared, because remember that matrix is 2 by 2. So we're scaling both rows by C. We have to multiply by C twice in the determinant. So we don't have a linear transformation because it violates the scaling rule. Now, we prove this with one specific example. Remember, if you're trying to prove that it's linear transformation, you have to check both and prove both for all possible inputs. To disprove that it's a linear transformation, all you have to do is disprove one property or even use a counterexample for one property at one specific valid input point. So for example, if we take the identity matrix, that's certainly a valid 2 by 2 matrix. If we multiply it by 2, then the matrix is 2, 0, 0, 2, right? The determinant of that's going to be 4. But if we just took the transformation applied to the identity matrix, the determinant of the identity matrix is 1. If we multiplied that by 2, we'd get 2, not 4. Therefore, the determinant, this transformation T, is a nonlinear transformation. Now let's look at 3 more operations to see if they're linear. First, the transpose. Does flipping a matrix over its diagonal preserve our rules? Well, first, yes, the transpose of a sum is indeed the sum of the transposes, so the first condition is met. And if you scale a matrix, the scalars just float along for the ride. Since both rules hold, transposition is linear. Second, what happens if we square a matrix? Well, this one actually fails immediately. If you scale a matrix by c and then square it, you get c squared times a squared, which is not c times a squared for any number but 1 and 0 for c. So you could try even with c equals 4. Definitely not going to match because 4 squared is 16. And so squaring a matrix is a nonlinear transformation. Finally, the inverse. Does the inverse of a sum equal the sum of the inverses? Well, not this time either. The inverse of I plus I, for example, is the inverse of 2i. So the identity matrix, if we take 2 of them and add it together, we're checking condition 1, right? That will be 2i. Then applying this transformation Q, which means we'll take the inverse of 2i, well, that is going to be the doubling every direction. We just saw if we have the matrix 2, 0, 0, 2, that's the same thing as multiplying both x and y to get the output twice as much. All right, so the inverse of a transformation is supposed to be doing the opposite of that. So what's the inverse of doubling every direction? It's halving every direction. So that's going to be 1/2 on the diagonal, then zeros on the off diagonal. That's 1/2 of the identity matrix. That is not what we would get if we applied the transformation independently to the identity matrices and added them together, which would give us, because the inverse of the identity matrix is the identity matrix, we get 2 times the identity matrix. So these are not the same result. We have a counterexample, and so the inverse is a nonlinear. Also, strictly speaking, this isn't even a valid transformation on the whole space, because the zero matrix, for example, has no inverse. If the zero vector breaks the machine, it is already game over, because for it to be linear, we have to make sure that the zero vector is mapped to the zero vector. But in this case, the zero vector is mapped to nothing, so Q is not even a valid transformation. Here's another neat example of transforming entire matrices with a real-life application. So let's test our rules on a specific function called a similarity transformation. We define this transformation, L of A, as S inverse times A times S, where S is this specific matrix 1, 1, 1, -1. All right, so to first prove number 1, we plug in A plus B. Because matrix multiplication distributes, we can split this into 2 separate terms, which simplifies to L of A plus L of B. So we meet the first check. Then to check the second one, scalars are just numbers. So if we plug in scalar C times matrix A, then we can take this C out of the matrix multiplication. It floats to the front. Then we'll get C times L of A, which is exactly what we wanted. So we have distributivity over scalar multiplication as well. Both checks are met, so this transformation is linear. Now let's see this in action. If we take, for example, the matrix 3, 1, 1, 3, you can check at home that the linear transformation applied to this matrix maps to 4, 0, 0, 2. All right, so we get this diagonal matrix as a result from this symmetric matrix. This is a similarity transformation, meaning it preserves trace and determinant. Okay, so here, the trace of the original matrix A is going to be 3 plus 3, which is 6. the trace of the new matrix is going to be 4 plus 2, which is still 6, right? The trace is preserved, meaning the same, after the transformation. All right, same thing with determinant. The determinant of the original matrix is going to be 3 times 3 minus 1 times 1, which is 8, right? The determinant of the new matrix is 4 times 2, which is also 8. So we have an L, which is a similarity transformation. Why do we care about this now? Well, remember, we resulted in a diagonal matrix. That's really special here. This is going to be a real-life application called diagonalization, which we'll learn about a little bit later. For example, what if we wanted a to the power of 1,000? Doing that many computations is going to be very messy and result in numbers that we might not even be able to get on the computer. But we could actually solve this by hand using this great technique. If we have a to the 1,000, if we were to write these specifically, if we have here, let's just add an s and s inverse right at the end. But if we have this one here, s inverse times a times s inverse times a times s, you see all of them will cancel. So you do indeed get 1,000 a's left over because, for example, s times s inverse is the identity that should cancel. So here you can see what we have is s inverse times a times s, 1,000 of them in the middle, then still our s and s inverse on the outsides. So what we know is this s inverse as, if we had a was 3, 1, 1, 3, that maps to 4, 2, which is a diagonal matrix, and diagonal matrices are special when we're taking powers because we can then, for this specific form of a diagonal matrix, just take powers of the diagonal elements. All right, so it's going to be 4 to the 1,000 times 2 to the 1,000, and if you'd like to check at home, if you multiply s by this one here, and then the original 4 to the 1,000, 0, 0, 2 to the 1,000 by s inverse, you do indeed get an actual solution, whereas a computer may not even be able to solve this depending on its number capabilities. And maybe you're watching this in a time where regular computers could easily solve, 4 to the 1,000. In that case, maybe try changing 1,000 to a Google. Can your computer still do it? If you do, that's amazing, and I'm glad you're living at that time. Now let's do a challenge example. Remember, vectors don't just have to be lists of numbers, they can be entire functions, all right? So let's define a transformation L from P5, which I'll define as the set of polynomials of degree at most 5, to P3, cubics or less, defined by this transformation, where we take a polynomial as the input and we output its second derivative. This is a linear transformation, all right? So you actually know this already from Calculus 1. First, to check the first condition, if we take two vectors and we sum them together and then we do the transformation, do we get the same output as if we took the individual transformations and then summed them? Well, yes, if we take two polynomials, p and q, and then we take their second derivative after we add them, we do get the same result as if we took the second derivatives of those polynomials first and then added those second derivatives together. All right, so for example, if you had p of x was 3x to the fifth and q of x was 2x to the fifth, their sum, p plus q, is 5x to the fifth, right? If you were to take the second derivative of that, you get 100x cubed. That's exactly what you'd get if you took the second derivative of 3x to the fifth plus the second derivative of 2x to the fifth. You'd still get 100x cubed. So we have met the first check. Now let's try and see the second check. Well, this is the constant multiple rule. If you multiply by a constant, the constant just sits there while you take the derivative. This works if you apply it 2 times for the second derivative. All right, so if we were to take a polynomial and then multiply it by c, then we take the derivative. That's the same as if we took the derivative and then multiplied by c. That's true for a second derivative as well. All right, so here's an example. If you take p of x is x to the 5 and c is equal to 2, well then c times p is going to be 2 times x to the fifth. the second derivative of that is going to be 40x cubed. That's exactly what you get if you took the second derivative of x to the fifth, which is 20x cubed, and then multiplied it by c, which is going to get you 40x cubed again. So because calculus follows these rules, very helpful. Differentiation, even second differentiation, is a linear transformation. And in general, for polynomials, for these that we're working with, polynomials will always have linear transformations for any derivative you could take. 5,000th derivative will still be linear. Now, instead of differentiating, let's try one where we evaluate the function. We define a transformation L that takes a continuous function and returns its value at 0. In plain English, this machine finds the y-intercept. Let's define L formally. It maps continuous functions to real numbers. Specifically, the real numbers generated are the y-intercepts of the functions being processed through this transformation. Is it linear? Yes. First, check addition. The y-intercept of a sum of functions is just the sum of their individual y-intercepts, because when we sum functions together, it's piecewise. It's at every x value, we'll take the y values and add them together. That x value could be 0. Then we verify this with lines. For example, if one line hits the y-axis at 3 and another hits it at 1, their sum will hit the y-axis at 4. Next, check scaling. If you stretch a function vertically by a factor of c, the y-intercept stretches by the exact same amount. Let's look at this graph for proof. The red cosine wave has a y-intercept of 1. If we double it to get the blue wave, the y-intercept jumps to 2. Since the intercept scales perfectly, this transformation is linear. Next up for this part, the definite integral. We define L as the integral from 0 to 3. Does it pass the addition check? Yes. The area under a sum of curves is just the sum of the individual areas. Our calculation confirms that integrating the combined function x squared plus x cubed with x values from 0 to 3 gives 36, which exactly matches the sum of separate integrals. Now, does it pass the scaling check? For any function and constant in the reals, if we multiply the constant first, do we get the same integral as if we multiplied the constant after doing the integration on the original function? Well, yes, this is the constant rule of integration, so it is true. And visually, we have an example. If you have a red box with a height of 1, the area, the integral underneath it, should be 3, right? If you scale the function by 2 to get the green box, the area becomes 6. Double the height at every x value, double the area. Since it behaves proportionally, integration is also linear. Now, let's start with the abstract definition of linear transformation L, which maps a vector space V to another vector space W. I want you to look at this diagram on the right. The box on our left is our input space V. Inside that space, we have the kernel, shown in blue. The kernel is the set of all input vectors that get squished or mapped directly to the 0 vector in the output space. The box on the right is our output space W. The green shaded area is the range. This represents all the possible outputs we can actually reach. Notice that the range is a subspace of the output space W, while the kernel is a subspace of the input space V. Now, let's make this concrete by using an M by N matrix A. Here, our inputs are vectors in Rn, and our outputs are in Rm. In this context, the abstract kernel is exactly the same thing as the null space of matrix A. It is the set of all vectors H such that A times H equals 0. Similarly, the abstract range is exactly the same thing as the column space of A. It is the set of all vectors Y that can be produced by A times X. Before we connect these further, recall what we discussed about mixing vectors. If you take all the rows of the matrix and mix them together using linear combinations, you create the row space. If you do the same with the columns, you get the column space. This leads us to a fundamental property of the domain. The entire input space Rn is actually composed of two perpendicular parts. The domain equals the row space plus the null space. This is crucial because it tells us that the null space and the row space are orthogonal complements. We'll have an entire lesson about that. Every vector in the input space can be broken down into the part that belongs to the row space and a part that belongs to the null space. Now, let's apply the definitions from the previous slide to a specific example. Here we have a 2 by 2 matrix A. First, let's find the kernel. Remember, this is the same as finding the null space. We set up equation A times x equals the 0 vector. When we solve this system, we find that x1 must equal x2. This tells us that our kernel is the span of the vector 1, 1. Geometrically, this is the line y equals x. Any vector on this line will be crushed to 0 by our transformation. And you could check. If you take a 1, 1 and you left multiply the matrix A, you do indeed get 0, 0. Next, let's find the range. This is the same as the column space. We need to see what linear combinations of the columns we can create. If you look at the columns of A, you'll notice the second column is just -1 times the first column, so they're actually redundant. Therefore, our range is spanned by just the first column, the vector 1, 2. That's the possible outputs we could get by doing the transformation L. All right, so geometrically, this is the line y equals 2x. I'd like to show you a visualization so you can see exactly what's happening to specific vectors. All right, so let's look at these graphs on the bottom. On the left is our input space, and on the right is our output space. First, look at the purple arrow. 1, 0 is mapped to 1, 2, and we see that is now on the line. Here, the red arrow, 0, 1 is mapped to -1, -2. That is now on the line as well. Now this last point, 1, 1, it is in the null space of the matrix, right? So it should be squished to 0. Anything on this blue line, if we apply this linear transformation, same as left multiplying by the matrix A, we'll get 0 vector. Now, I have a bonus tip on how to intuitively break down a transformation. We have the same matrix A as before, but I factored it into two separate matrices for you. Now remember, we read matrix multiplication from right to left, just like composite functions. So we apply the matrix on the right, which we'll call P first. Okay, so matrix P is a projection matrix. As you can see in the first grid, it takes our entire 2D space. What does it do? It flattens it via orthogonal projection onto the line y equals -x. Now, this is that exact animation. You see we lose a dimension. All right, now that our world is just a flat line, then we'll apply this second transformation, also linear because it's left multiplying by a matrix, right? That we'll call S. That one takes the flattened line and rotates and scales to give actually this same output as our output space. Okay, so you can decompose these into two different transformations that result in the true result. Okay, fun fact, this is also a way to find examples of rare commutative matrix multiplication. If you can swap the order of transformations, then the matrices commute. These matrices don't commute because if we were to do the rotation and scaling first, then squash with our orthogonal projection, different points would have different results. Next up, let's talk about when things break. Here we have the matrix P from the previous slide. That's the projection, right? We can calculate the determinant of P, and it comes out to exactly 0. So you likely saw that the determinant 0 means not invertible, but graphically this tells a much more interesting story. So here, watch this grid on the left. Remember, because the determinant is 0, the area of our grid collapses to 0. The entire 2D plane gets squished onto a single 1D line. All right, so the determinant is going to be the area of this 1 by 1 box. What is that in the end? It ends up being 0 because we deleted a dimension. And so the inverse is trying to undo. All right, so look at this diagram on the right. If I give you an output of a point on this line, say -1, 1, do you have a way of knowing where it came from? Can we undo this transformation to get back to the past? Well, did it come from 0, 2? Did it come from 1, 3? There's no way of getting one unique input that mapped out to give us this output. So here's a video of me trying to undo the transformation by left multiplying space by p inverse, but you see we have infinity outputs for each input. It's not going to be a function. So because we smashed all those distinct points into the same spot, we destroyed the history of the vector. Therefore, no inverse exists. Now, another critical takeaway I'd like you to keep, because it's special, is that the inverse of a matrix is the undo of the transformation obtained by left multiplying by that matrix. Now, let's look at a happy case where nothing breaks. We have a new matrix A, which is just a 90-degree clockwise rotation matrix, as seen earlier. When we check the determinant, we get 1. This isn't 0, which means we are safe. We haven't collapsed any dimensions, so we are allowed to have an inverse. We always take an output, and we can find what input gave us that output. So let's look at that transformation L first. If you plug in the unit vectors, you will see that A acts as a rotation, and that's exactly what's happening for us on the grid on the top right. The entire world rotates 90 degrees clockwise. Since the grid lines didn't squash together, we haven't lost any information. We can always undo. All right, so let's see. We can always define a new function k to get it back. That uses the inverse matrix, right? So watch this bottom grid. The inverse matrix effectively rotates everything 90 degrees, or pi over 2 radians, counterclockwise. It rewinds the movie, taking every vector back to its original starting position. So if you apply both, you get the same transformation as the matrix, which applies the identity matrix. All right, so I'll leave you with a quick puzzle to try at home. Can you find 4 different matrices that, when you chain them all together, loop you back to the identity? Just kind of fun thing to try. All right, great job, and I hope you have a wonderful day.